Good afternoon, everybody. Welcome to today's algebra seminar. And today's speaker is Ehud Meir from University of Aberdeen, and he will tell us about monoidal categories and algebraic structures. So please, Ehud.
Thank you very much. Thank you for the invitation. So, as the title suggests, I will tell you mostly about algebraic structures in monoidal categories. The first part of the talk, I would like mostly to give an introduction to monoidal categories, the way that I understand them. And it will mostly be about symmetric monoidal categories, but not only. In the beginning, I will also tell you about braided ones. Okay, so first of all, categories, what is the framework? So you all know a category C has objects and some morphisms between them. And usually it describes some sort of structures with maps that preserve the structure, like vector spaces and linear maps, groups and group homomorphism, topological spaces and continuous maps, and so on. However, many interesting categories admit much richer structure than just objects and morphisms. And the one I will concentrate about today will be that of monoidal categories, and in particular, symmetric monoidal categories. Okay. So what is a monoidal category? A category C is called monoidal if it's equipped with a functor, which is called the tensor functor from C times C to C. So from any two objects of C, we can generate a new object of C, such that the following condition holds. So for every A, B, and C, we have an isomorphism alpha from A tensor B tensor C to A tensor B tensor C. So in other words, we say that the two objects, A tensor B tensor C and A tensor B tensor C are isomorphic, but there's also a specific isomorphism between them. And we have a tensor unit 1 together with unit isomorphisms. So tensor in with 1 is actually isomorphic to just not doing anything, both from tensor in from the left and from the right. And last thing, and quite important as well, is that some coherence conditions must hold. And I guess the most important one is the one in the next slide that's written here. So in other words, if you start with this A tensor B, tensor C, tensor D, where all the parentheses are to the left, and you move it, you can move it in two ways to the right to A tensor B, tensor C, tensor D in two different ways, then it should give you the same morphism in the category. Okay. So important thing to notice here is that usually when, let's say, we speak about groups or about rings or anything like that, associativity and unitality are just a condition. Like you just say that in a group A times B times C is equal to A times B times C. And here, what happens is that they are also a structure because we really need to give the specific isomorphism. And this makes everything more complicated. We need this diagram to be commutative. So in a way, we got into a one level higher of a condition. Okay, now, so we spoke about monoidal categories, and a monoidal category is called braided if it is equipped with a collection of isomorphisms, sigma AB from A tensor B to B tensor A. And as before, they should satisfy something. So we write this kind of diagram for sigma AB, going from A tensor B to B tensor A. And these isomorphisms should satisfy the so-called braid relations that just say that if I go from ABC to BCA by first taking A and jump over B and then over C, it's the same if I just take A and jump immediately over B tensor C. And same thing when I look at what happens with the C string on the other side. Now, here's a question that arises here. Is a braided category commutative in any way? So, well, we have seen that in a braided category, we know at least that A tensor B is isomorphic to B tensor A. So it's important to say that this is actually, that braiding is an extra structure, not just a condition of saying that A tensor B and B tensor A are always isomorphic to one another. And in fact, so one thing that you would expect to happen, but doesn't always happen with this category is that if you consider the map from A tensor B to B tensor A to A tensor B, of doing the braiding twice, then it will in general not be the identity on A tensor B. Okay, so a braided monoidal category is called symmetric if it does hold. If it does hold that when you do the braiding twice, you get to the original thing, just the identity of B tensor A. Okay, so this was just some definitions of categories and categories enriched with some structures. And now I would like to give you some typical examples of these things. Also some examples for which I will use in the second half of the talk. Okay, so we shall only consider here categories in which the home spaces are finite dimensional K vector spaces. And the most canonical example for a symmetric monoidal category that you should keep in mind is the category vec K, and this is the category of finite dimensional vector spaces over K. Another example is the category of supervector spaces, and this is the category of finite dimensional supervector spaces, which means that we have vector spaces that are graded by 0 and 1. So every vector space there can be written as V0 direct sum V1. And the main difference from the category of vector spaces is that the grading is different. It changes by a sign. So when we take V tensor W, let's say that both V and W are in degree 1, in V1 and in W1, we don't say send it to W tensor V, we only send it to W tensor V multiplied by -1 to the degree of V times the degree of W, which, if they're both in degree 1, will be just minus W tensor V. Okay, so this is an example of a slightly different braiding, given though when we think of vector spaces, it's very clear how to do this transition. There are sorry, other ways to do it as well. Okay, so other useful examples. If we take a G to be an algebraic group, we can look at the category rep G. This is the category of all finite dimensional algebraic representations of G, so those that you can really write using polynomials. And this is an example of a symmetric monoidal category. The action is just the action on V tensor W is just given by the diagonal action, G tensor G. And one last example is that if we have a Hopf algebra H, we can take the representation category of H, and this will give you a monoidal category, but usually this category will not be braided. And there are some special kind of Hopf algebras for which you get a braided monoidal category. They're very interesting in their own, for their own sake, but as we shall soon see, the only intersection between these two is really, the only case where rep H is actually symmetric, it is when it is rep G. I will mention this theorem of Deligne in a few moments. Okay, let's see another flavor of example of how we can construct such categories. So let's say that G is a finite group, and we can consider the category vec G of finite dimensional G-graded vector spaces. So how does this look like? Objects are G-graded vector spaces. So these are all V that I can write as the direct sum of V sub G, where G is in G. So in other words, every element you can split into G homogeneous elements, into G homogeneous components, let's say. The morphisms are just linear maps from V to W that satisfy that they take the G homogeneous component to the G homogeneous component. So the G homogeneous component in V to the G homogeneous component in W. And the tensor product, here is the point where we actually use the multiplication in the group G. The tensor product is given by V tensor W sub G is the direct sum of VA tensor WB, where AB is equal to G. So in other words, if you take something of degree A, you tensor it with something of degree B, you get something of degree A times B. That's the rule here. Okay, and in all, one thing that's important to say is that in all the examples we gave so far, the associativity was kind of obvious in the sense that it was kind of clear how to go from A tensor B tensor C to A tensor B tensor C. But this was in a way more of a lucky coincidence than actually a promise to the future that it will always be this way. So just as an example for this category vec G, we have here actually many different choices of associativity that will really change the category as a monoidal category. Okay, so how can we construct any other kind of associativity? So if we have a free cocycle omega going from G cube to K star, K is the ground field, we can define associativity, again, going from V tensor W tensor U to V tensor W tensor U by sending V tensor W tensor U to omega of ABC times V tensor W tensor U. So it's the usual, in a sense, it looks like the usual associativity, but we multiply it with this element omega. And then when you look at the diagram we had in the beginning, this hexagon diagram, the commutativity is actually exactly equivalent to saying that omega as a function satisfies the identity of being a Frico cycle. Okay, and this gives us really a different category, vec G omega. So it's important to say that the monoidal category, we don't only need the tensor product, we also need the associativity. And therefore, this vec G omega for us, it's as long as omega is not trivial, it's a different symmetric monoidal category. It's not necessarily symmetric. Now, okay, we also spoke about braiding, so we might ask, will this thing be braided? So one obstruction that we need is that the category vec G omega can be braided only when G is abelian. Because if when G is not abelian, take two elements A and B that do not commute with one another, yeah, and just you will notice that the formula for V tensor W is not symmetric. It's not that you have some obvious isomorphism between V tensor W and W tensor U. I mean, because things are here are a bit more complicated, and we also use this kind of higher level thing, we also use structures and not only conditions. So it is possible that for some abelian G, non-trivial omega, it might happen that vec G omega will have no braiding. Okay, when G is abelian, it is important to say that when omega is trivial, vec G is always braided, and we can even describe the different braidings because again, it's part of the structure. So what happens is that possible braidings are in one-to-one correspondence with bicharacters, psi from G times G to K star. And the bicharacter psi defines a symmetric braiding if and only if it holds that psi AB times psi BA is 1 for every A and B in G. In other words, if and only if psi is not only a bicharacter, but also a skew-symmetric bicharacter. Okay, so how should we think about all these categories? So deep inside all the categories we mentioned so far, they want to be, in a way, the category of vector spaces, or at least a category of vector spaces with some extra structure, like that an action of a group, an action of a Hopf algebra, a gradient by a group, and so on. Okay, however, the thing is that some of these categories succeed more than others in being categories of vector spaces with some extra structure. What exactly do we mean by this? We will soon see. So actually, the particularly successful one are the symmetric monoidal categories by a theorem of Deligne that I will now tell you about. Okay, before I continue, maybe are there any questions so far? If not, then okay. So I would like to tell you, so the theorem of Deligne is a theorem of the form, let's say, be a symmetric monoidal category that satisfies this condition and that condition. Then necessarily it's the representation category of some algebraic group or some direct union of algebraic groups. Okay. So let's say now be a braided monoidal category and let V be an object in C. Now let's see what happens. We can consider the object V tensor N, which is just V tensor V n times. And here's one very important piece of structure that we always get in braided monoidal category. We can apply sigma VV to the adjacent tensor powers of V. So like the first one and the second one and the third one, the n minus first and the nth one, and so on. And this will define as a group homomorphism from the braid group Bn to the automorphism group of V tensor N, the automorphism inside the category C. Here Bn is the braid group on n strings. Okay, so the braid group has this presentation S1, S2 up to N minus 1 with some relations that do hold here, and we do get group homomorphism, and we can think of it as saying that Bn acts on this object of C in this way. Now, if C is also symmetric, then we are in a very nice situation, because then this homomorphism splits as via the quotient Bn to Sn to the automorphism group of V tensor. So let me just give you an example. So if we are looking at a vec K or rep G, this action for sigma in Sn is just given by this formula, that sigma of V1 tensor V2 tensor Vn is V sigma inverse of 1 tensor tensor V sigma inverse of n. Okay, so we just tensor permute the order of the tensors. And because in a symmetric monoidal category, we know that sigma AB, sigma BA is the identity, this really gives us an action of Sn, of the symmetric group. Now, why is this good for us? So because we assume here that everything is K-linear, what we actually get is an algebra homomorphism from KSN to the endomorphism algebra inside C of V tensor n. And this is good because once you not only have Sn, but you also have KSN, you pass from talking about group actions to group representations, right? And then you can just say, okay, I understand KSN as a finite dimensional algebra. I know that it splits in a certain way to direct sum of matrix algebras by the Wedderbrunn decomposition. And then the good thing is that we have a very well-studied representation theory of the symmetric groups. And we can use this in order to study the category C, whatever the category C is. So as long as we know that C is a symmetric monoidal category, representation theory of symmetric group can be applied there. And this is very useful for us. So here is one example. We can consider the image of this idempotent in the group algebra of Sn, 1 over n factorial times the alternating sum, -1 to the sigma times sigma. -1 to the sigma, I mean here the sine of sigma. And the image of this idempotent is just going to be the nth exterior power of V. Okay, just before I continue, I just want to mention that one important feature of this, that I would like you to notice now, is that if I consider these kind of idempotents for different n's, then if I just start with some vector space V or some group representation V, once I take n big enough, then this thing will just be 0. Right? Because, well, you know, for finite dimensional vector spaces, the exterior algebra is finite dimensional. From some point onwards, it's just 0. Okay. Now, another thing that we need in order to, another concept we need in order to state the theorem of Deligne is that of dual. So if we have an object in a monoidal category, and this works for any monoidal category, not only symmetric or braided one, we can say that a dual V star of V is an object of C for which there are morphisms of evaluation V star tensor V to 1 and co-evaluation from 1 to V tensor V star. And they should satisfy the following axiom. If you haven't seen this before, this is not so bad. It doesn't matter so much. Just keep in mind that this evaluation of V, this is just a linear map that sends F tensor V to F of V. One here is the tensor unit, and it's just the ground field K as we care. Co-evaluation is the map that sends 1 to the sum of EI tensor EI, like a dual basis kind of thing. Okay, and this kind of axioms is just another way to say that taking tensor product with V and taking tensor product with V duals are adjoint functors to one another. Okay, so this is just a categorical way to view duality of vector spaces. So we will say that C is rigid if every object has a dual, which actually does happen in all the examples we have seen so far. For example, okay, for finite dimensional vector spaces, you know that you can just take the home space into K. If you take a group representation, then you know that the dual is automatically also a group representation. It also works for FH. It also works in the category vec G omega that we mentioned. They all have duality.
Sorry, can I ask a question?
Yes.
Sorry to interrupt.
Yes.
So in this case that it's a rigid category, Does it, maybe it's obvious, but is it clear then that taking dual becomes actually a functor?
It's not completely obvious, no, but we can. Yes, you're right. I mean, we, properly speaking, we need to make some sort of choice. Like we need for every object V to choose V star with this evaluation, co-evaluation. But once we do this, it works.
Okay, it becomes a functor.
Yes.
Automatically.
Yes, it becomes a functor. Yes.
Okay, thank you.
Thank you. Any more questions? If not, then let me say what is this theorem of Deligne. So what Deligne showed was the following. Let's assume that C is an abelian rigid symmetric monoidal category with finite dimensional Hopf spaces. So by abelian, I mean that we have direct sums, we have kernels and co-kernels. We can talk about sum of morphisms and so on. And assume that this condition that I mentioned before holds. Assume that for every object V in C, there is an n such that the nth exterior power is equal to 0. Just like happen in vector spaces and just like happen in, let's say, representations of G. Then he showed that there is a group G such that the category C is equivalent to rep G, a symmetric monoidal category. Okay, so just by knowing this condition, he managed to show here's a group G, and here's an equivalence between C and the category of representations of this group G. If, moreover, the category C is finitely tensor generated, then G is an algebraic group. Okay, so it will be something like, think about it as a Zariski closed subgroup of GLN. Yeah, it can be, for example, ON, SP, 2N, and so on. Now, what's the idea? I want to give you some idea about the proof, and just to give some background to this. So the good thing about these rigid symmetric monoidal categories, and this is really better situation than what we have in graded monoidal categories or just monoidal categories, is that we can pretty much freely do linear algebra in them, and we can also do some commutative algebra. And as a result of commutative algebra, we can also do some algebraic geometry. And this is kind of the way that really algebraic groups come into the picture. Okay, so here's the thing. We can talk about algebras inside C, commutative algebras inside C, and also modules over there. For example, what is an algebra when in this particular context? So an algebra A in C is an object with a morphism M from A tensor A to A. Right, this is the usual way that we define what is an algebra when we speak about, like, let's say, if A is a vector space. Of course, if we want it to be associative, then we need to require some equality between composition of morphisms, like M times M tensor 1 is equal to M times 1 tensor M. A unital algebra is an algebra for which we have a morphism U from 1 to A such that this condition holds. Okay, so such that M times 1 tensor U is the identity map. Point being is that the usual things that we have when we talk about algebraic structures in VEC, we can really phrase it in categorical terms. We can say instead of linear maps, we say we have morphisms. Sorry, and yeah, instead of axioms, the axioms basically boil down to some compositions of the morphisms are equal to some other compositions. And the multiplication M is commutative if M is equal to M times sigma AA, where sigma AA is just replacing the two entries of A. Okay, now we can also talk similarly about modules, A modules inside C. So an A module M in C is an object of C together with a morphism from A tensor M to M, such that the usual module axioms hold. Again, this kind of associativity and so on. Sorry. Now, if A is a commutative algebra inside an abelian symmetric monoidal category C, then the category mod CA, or the category of A modules in C, is again a symmetric monoidal category. And here the tensor product is given by taking tensor product over A, which is possible to do because it's a symmetric monoidal category and it's relatively straightforward. And one important aspect of this is that we get a symmetric tensor induction functor. Going from C to the category of A modules in C, it's kind of taking the free module over V, we take V to just A tensor V. Okay, so the idea of the proof of Deligne is that he constructed a fiber functor or a tensor functor, a symmetric tensor functor from C to vec K, the category of vector spaces. Then he recovers the group G as the group of automorphisms of this functor. Again, because we can think of a functor as an element in some category. So automorphisms mean natural automorphisms going from f of v to f of v for every v. Now, to construct the functor f, how do we do that? We do the following. So we start by taking any object v of the category. We construct a commutative algebra A inside the category such that the A module, the induced module, A tensor V, actually splits as A tensor 1 plus some other object, V prime. And then we continue constructing more and more and more algebras until we reach an algebra A that satisfies this, that the A tensor V is just A plus A plus A plus A plus A for some n, for every V and C. The reason why we can do that, so, okay, so I need to say that to do this part of the construction, to find the commutative algebra such that this holds, this is something that we can do quite generally. But in order to reach this point, that A tensor V is A to the n, we really need to use the condition on the exterior powers of V that we assumed in the theorem. Good thing is that just by taking this now very big commutative algebra in C, we get this kind of induction functor from C to mod CA. But in fact, the image of this functor lands in a much smaller subcategory of mod CA. It lands in a subcategory of modules over some concrete algebra, where this algebra is the algebra of is home C from the unit object to A, which also carries an algebra structure by the multiplication in A. Okay, so why is it good? Because then we use an algebra homomorphism from B to K to get a functor from this category to vec, and altogether we get a functor from C to mod vec B to vec. We need to make some extra technical assumptions that I will not talk about here to make sure that that everything is fine and that we really get a monoidal functor that is also exact and so on. But this works, and this enables us to really get this fiber functor from C to vec K, and then we can recover G. Important thing to say here is that when we say that we use an algebra homomorphism from B to K, we really use the fact that K is algebraically closed, because otherwise we don't necessarily have a homomorphism from B to K. This B here is going to be some sort of finitely generated commutative algebra, or at least a union of finitely generated commutative algebras. So we use kind of Nullstellensatz in doing this. I would like to give one example for this thing. So let's consider the category representations of GL1K. Oh, this is just the multiplicative group of K. So how does it look like? How are the algebraic representations look like? So this category is actually semi-simple, which means that every object can be written uniquely as the direct sum of simple objects. And the simple objects are in one-to-one correspondence with elements of Z, where for n in Z, the simple module, the simple object Sn is just K, one-dimensional representation, where the action is given by lambda acts on X by multiplying by lambda to the n. Okay, so we just have different weights basically here of this lambda. There is, of course, this is a very, very trivial case of the more sophisticated theory of representations of SLNK and GLNK. But here the good thing is that we can relatively easily describe what's going on. Now, the algebra that I mentioned that we create, we take the symmetric algebra on the direct sum of S1 plus S minus 1, and we divide by the relation that's saying that V1 times V minus 1 is equal to 1. So this all sounds very just like I'm doing things inside the vector spaces, but actually this algebra is something that I can define purely in categorical terms inside the category of rep GL1K. The beauty of this is that it then holds that Sn tensor A is just isomorphic to A, and then if I take B, which is what I say home C1A, this is just K, the ground field, and then induction functor just gives us already a fiber functor from C to vec K. Just as simple as that. So we just need to choose the right algebra, and in the case of GL1K, we are also in the relatively fortunate situation that it ends quite quickly. For most categories, this procedure will be much longer. Okay, so let's see what this means. It means that any abelian rigid monoidal category in which the exterior power vanishes for n big enough, we can interpret as a category of vector spaces and linear maps with some extra structure. That is that of representations of some group. And then we can ask, okay, but then what happens when the condition that the exterior power doesn't vanish? What happens when the condition about the exterior power doesn't hold? What do we do now? Do we even have such examples? So the answer is that we actually have a lot of such examples. And first of all, what Deligne studied chronologically was categories in which every object is annihilated by some sure functor. Okay, so sure functor are kind of, you can think of them as some generalization of this exterior power. We also multiply by some idempotent coming from the coming from the group algebra of Sn, as we did with this particular one. And such categories, they admit a fiber functor not necessarily to vec K, but to super vector spaces over K that we mentioned before. But in fact, there are even more general categories, and this is mostly what I will talk about in the second part of the talk. So we have the categories rep ST that there will be some examples for interpolation. And here's the thing, we can consider Sn and the representation categories rep Sn. So of course, all these categories, they are rep G for some group G. I mean, specifically for G is equal to Sn. But here's the thing that we can kind of, you can kind of think of them as rep S1, rep S2, rep S3, and so on, somehow on, let's say on the complex plane. And you can just fill in the entire complex plane with such categories where, in particular for t is equal to n, you get rep Sn. So how does this go? So Deligne showed that these categories admit a uniform description. He gave a list of objects that make sense in rep Sn for every n. In particular, xm, he described it, it's the linear span of the injective maps from 1 to m to 1 to n. So for most, I mean, if you fix an n for most m, this would be 0. And then he also showed that the home spaces can be described uniformly independently of n, and that the coefficients of the compositions are polynomials in n. And then you say, okay, so if this is the case, I can just define formally my object as kind of direct summands of these xn's. Compositions and tensor product will be given by polynomials in n, but then polynomials that are polynomials in an integer, we can also interpolate for all complex values or all values in k, right? So this enables him to define abstractly the categories rep st, also when t is not an integer. So even though, like, let's say if I tell you the symmetric group on 2 plus 1 over pi elements, and that doesn't make much sense, the representation category of this group that doesn't exist does make sense. So we do have an object called rep st also when t is not an integer. Yeah, so Deligne also interpolated other families of symmetric monoidal categories like rep GLTK, rep OTK, and rep SP2TK, and I will mention them in the second part of the talk. Okay, so important thing to say is that these categories admit a fiber functor that is a tensor functor to vec only when t is equal to n. Otherwise, they do not satisfy any condition like that every object is annihilated by some sure functor. The growing of elements is very weird in these categories. Only when t is equal to n, we really get something familiar. Otherwise, we get something quite wild, or relatively wild. But still, however, with no tensor functor to vec. Okay, so in the next part of the talk, I will tell you about using invariant theory to interpolate category and to study algebraic structure. So, okay, in this second half, I will talk more about my own work. The previous part was pretty much an introduction, especially to this theorem of Deligne. Yeah, so now I will introduce some new things. I will talk about general algebraic structures in monoidal categories, and also how we can use invariant theory to study them. And I guess the main difference is that in the first part of the talk, I kind of gave examples of categories that one kind of just find in nature, let's say. And in this part, we will do more things like constructing examples of symmetric monoidal categories, including those of Deligne, but some others as well. Yeah, let's start. Okay, so we will talk about, as I said, invariant theory, some universal ring of invariants, and construction of symmetric monoidal categories out of characters of this. Lastly, I will show some examples. Okay, so we continue with the field K that is algebraically closed and of characteristic 0. And our framework will be that of finite dimensional algebraic structures over K. So examples are, let's say, algebras or Hopf algebras, comodular algebras, Frobenius algebras, co-algebras, everything that you can write using a finite dimensional vector space and some structural tensors between them. Okay, so what do I actually mean by this? So they are given by some vector space A, finite dimensional one, and a finite set, I assume, of structural tensors, which are maps going from some tensor power of A to another tensor power of A. So if it goes from A tensor Qi to A tensor Pi, we will call this set of numbers Pi Qi the type of our algebraic structure. And we will assume that it is fixed throughout this part of the talk. We will write symbolically the structure tensors like this. So M, for example, is multiplication. It goes from A tensor A to A, so it has 2 legs and 1 output strings. While delta, it goes from A to A tensor A. This can be co-multiplication in Frobenius algebra or Hopf algebra. And it goes from, it has 1 leg and 2 ends in the air, or 2 output strings. Okay, so for example, a unital algebra has type 1, 2, 1, 0 because we have one box which is this M going from 2 to 1. So this is the 1, 2. And we have U which goes from no legs to 1. So this is the 1, 0. Now the structural tensors usually satisfy some axioms like associativity, or if it's a Lie algebra, then Jacobi identity and so on. And the important thing is that these axioms can be written using diagrams. So here is, for an example, how I write associativity. Okay, so to say that something is associative, I just say that these 2 diagrams, the difference between these 2 diagrams is equal to the 0 transformation between going from A tensor A tensor A to A. Now, here's a very general question. Can we classify algebraic structures of a specific type, like algebras, or maybe those that satisfy some specific set of axioms, like, let's say, Hopf algebras, Lie algebras, and so on? And we know that, in general, this is a very difficult question. There's a lot of work on this, but it's very hard to say something very general. So what I would like to tell you about is how to approach this problem by using tools from what is known as geometric invariant theory. Okay, so let's start. We want to get some invariants for our structure. So the first invariants that algebraic structure have is just the invariants they have as vector spaces, which is their dimension. So in other words, if we have, let's say, one algebra of dimension D1, one algebra of dimension D2, and D1 is not equal to D2, then they are not even equivalent as isomorphic as vector spaces, so let alone not as algebras. And we know that A1 is not equivalent to A2. Okay, so let us fix the dimension D. Let's assume it's a finite dimension, as we said. And now we can ask something more specific. Can we classify algebraic structures of specific type of dimension D? And maybe let's ask a slightly refined question. What is an algebra of dimension D? And let's see now how we can answer this using algebraic geometry. So here's an answer, one possible answer. We can choose, and I emphasize here choose. I cannot emphasize this strongly enough because this choice is going to be very important. Let's choose a basis E1, E2 up to ED for the algebra. And then the multiplication M, which is just a linear map from A tensor A to A, is given by the structure constants Mijk. So M of EI tensor Ej is the sum of Mijk, Ek. Okay. So in this case, we can think of the multiplication just as a collection of numbers, as d cube numbers, or alternatively as a point in the of this a to d cube. Okay, and then specifying a property such as associativity or commutativity is just given by a set of polynomial equations on these numbers. Okay, so for example, associativity is given by this kind of polynomial equation, quadratic polynomial equations, when we try to evaluate multiplication on ei tensor j tensor k. Commutativity is simpler. It is just a bunch of linear equations saying that mijk is equal to mjik. And we can apply the same principle to more complicated things like Hopf algebras, Lie algebras, Frobenius algebras, and so on. Okay, so in this way, we basically translated everything to algebraic geometry, right? Because we now think of this as points in some affine variety. Now, here's a serious problem, is that the structure constants are not unique. Remember, we said earlier that we choose a basis. Once we choose a basis, we have the structure constants. Okay, but this is exactly the point. They depend on this choice that we made. And let us rephrase this in a way. So in the algebras example, we have a subset y in a to the d cube, where I are all the associative multiplications. We have an action of GLDK on this variety on a to the d cube, just given by a change of coordinates or a change of basis. And this action restricts to y. And what we really want to understand is the set of orbits, y modulo GLDK. Because the thing is that 2 points will be conjugate under the action of GLDK if and only if they define isomorphic algebras. And invariant theory gives us exactly the tools to study this type of quotients, this y modulo GLDK. Okay, any questions so far? If not, then let's continue. Okay, so how do we actually do it? So we fix a type PIQI. We write UD for the affine space made of the structure constants for structures of dimension D of this type. So previously it was just a d cube, but it can be something much bigger. We have an action of GLDK on UD. And we have this theorem of Montfort that's saying that there is an affine variety XD such that the ring of invariants, KUD, to the GLD is equal to the ring of polynomial functions on XD. And the points in XD are in one-to-one correspondence, not with all the GLD orbits in UD. That's impossible, and we will soon say why, but only with the closed GLD orbits inside UD. Okay, so in particular, one way that we can think about it is that the invariants in KUD to the GLD form a complete set of invariants for closed orbits. That is, if we have 2 points in 2 different closed orbits, then we have an invariant that separates them. Okay, why, by the way, let's just say, why does it make sense that the ring of invariants arise here? Because you can think of the invariant functions in KUD to the GLD as functions that are remain constant on every orbit. And therefore, they are kind of the algebra that you would expect to find as the algebra of functions on a quotient space, if a quotient space exists. In general, constructing quotient space because of this problem of non-closed orbit is kind of one of the main difficulties that one encounters in studying geometric invariant theory. Okay, so this is the story, and now I would like to give you some examples that you have seen in some point for use in geometric invariant theory. And the first one is something that you have all seen in school in Euclidean geometry. We didn't really call it geometric invariant theory at that point, but it's kind of what it is. So one of the main questions that you have in Euclidean geometry is, let's say you have 2 triangles in the plane, and when does it happen that they are congruent to one another? Okay, like you have this delta 1, delta 2, when are they congruent? And by congruent, we mean that you can get from one to the other by translation, by rotation, and then maybe by reflection as well. In other words, we have X is the set of triangles in the plane, gamma is the group of O2 same-direct product R2. R2 is for translation and O2 is for rotation and reflection. And we ask, what is the quotient of X mod gamma? Okay, what are all the equivalence classes? or what are all the orbits. In this case, we have the well-known side-side-side theorem, which tells us that delta 1 is congruent to delta 2 if and only if the set of sides A, B, C is equal to A prime by B prime C prime. Okay, so in other words, we do get in this way a kind of set of invariants, set of numerical invariants that enable us to say exactly when two things are congruent and when they are not. Another example, this is from linear algebra. So one of the main things that we try to do there is to classify all linear transformation up to conjugation by an invertible matrix. So all T from K to the D to K to the D up to conjugation. In other words, we want actually to study the quotient of all D by D matrices divided by the action of GLDK by conjugation. Okay, so in this case, the answer to what is the ring of invariants is actually well known. In this case, this is just polynomial rings in D variables, C1, C2 up to CD. Well, what are these variables? So C1 is the trace, CD is the determinant, and everything in between are just the coefficients of the characteristic polynomial of T, of this T. Okay, so think about it like this. You do know that trace of a matrix doesn't change by conjugation, determinant as well, and all the coefficients of the characteristic polynomial, they also don't change under conjugation. But in fact, it's more than that. They are all algebraically independent, and they generate the ring of invariants that we have here. Okay, so this polynomial algebra also has another useful basis that we will see some things like that a bit later. So we can also write that it is generated by trace of T squared up to trace of T to the D. We have this kind of, at least in characteristic 0, this kind of transition matrix between these bases and that basis over here. However, it's important to say that orbits are not closed, and we cannot distinguish, for example, the orbits of the 0 matrix and this matrix, 0, 1, 0, 0. Right? I mean, think about it. So trace and determinant of this thing are 0, and trace and determinant of this nilpotent matrix are also 0. Okay, and why does that happen? This is because the orbit of 0, 1, 0, 0, it contains all the matrices 0, x, 0, 0. And then what happens is that it has also the matrix, the 0 matrix, it has in its closure, right? Because even if we have just the matrices 0, x, 0, 0, when we take the limit when x goes to 0, we get the 0 matrix. Okay, so this is roughly, schematically, how this thing looks like. Okay, so the green orbit is on the boundary of the blue orbit. So just by the continuity of invariant polynomials, we cannot distinguish them, and it's really not so surprising that that the trace and determinant we get are the same for the nilpotent matrix and the 0 matrix. And still important to say that a lot of us spend a lot of time teaching linear algebra and concentrating on finding eigenvalues and the characteristic polynomial, because this actually does give quite a lot of information about what's going on with the matrix. And even if it doesn't describe them, even if there are different Jordan blocks, let's say, there are different types, still it gives a lot of information about the matrix. Okay, any questions? Not so. Let's continue with non-closed orbits. So if we try just to use very directly this technique to study, for example, associative algebras, like the variety Y we mentioned before, we reach a dead end pretty quickly. And why is that? And this is because the 0 multiplication is in the closure of every other orbit. Okay, if we just rescale our basis elements by lambda in K, we get something like this, that we change the mijk by lambda, and then we take the limit when lambda goes to 0, we just get the 0 multiplication on the boundary. Okay, so we want to kind of avoid this. As a result of this, the ring of invariants is really not interesting. It's just a ground field itself. It gives us no information. However, the more complicated algebraic structures we have, the more invariants we actually get. Okay, and this is what we are going to do. We're going to explain what kind of invariants we get. So first thing is that if we have any two natural numbers p and q, we can form constructible maps from a tensor q to a tensor p. And here is one example with p and q equal 2 and 3. Okay, let's say that we have this kind of boxes of the type M and delta. So M is type 2, 1, delta is 1, 2. Sorry, M is 1, 2, and delta is 2, 1. And we can do something like this. So here you see that we flip the two entries of M, then the output of this M goes as the input of this M, the output of this delta goes as the second input of this M, and so on. So in other words, what do we mean by constructible maps? We mean that they are constructible from the tensors M and delta by first taking tensor product, which just correspond to putting things one next to another. We can apply tensor permutations like we have done here, yeah, with the two legs of M. And we can connect input and output strings, and this corresponds to applying the evaluation that was mentioned before. And in particular importance, we have closed diagrams where P and Q are equal to 0, 0. So in other words, we have no free strings. They are all closed and all connected to one another. And such diagrams, they represent linear maps from A tensor 0 to A tensor 0, from K to K, and these are just scalars. So here's one example representing the trace of the composition of delta with M. We have this kind of thing, and you see that it's closed. There are no free legs or no free hands for this thing. Okay, and every closed diagram, this is the important thing, it gives us a scalar invariant. That is, if you have any vector space A together with maps M and delta, as described here, you can just form this diagram. You can calculate the trace of delta composition M. This will not depend on any particular choice of your basis for A. It will always give us the same answer, and it gives us a scalar invariant of delta and M. Okay, so now we do the following. We write con PQ for the free vector space spanned by diagrams of constructible maps from A tensor Q to A tensor P. When we look at all the constructible maps for any P and Q, this is equipped with some useful structure. For example, we have tensor product, going from con AB, tensor con CD to con A plus C, B plus D. We have pairing, that is quite useful. So going from con PQ, tensor con QP to con 0, 0. And schematically, just given by, if we think of these two as maps, we can take their composition and take the trace of the composition. So schematically, we can write it like this. If we have, let's say, D1 and D2, we connect the output strings of D1 to those of D2, and the output of D2 to the input strings of D1. And we get a closed diagram, and this just gives us a number or an element in con 0, 0. Okay, so in particular, what we get is that this con 0, 0, the linear span of closed diagram, this is actually an algebra. How does the multiplication look like? Well, we just take two diagrams and we can just put them one next to each other and get a bigger, even if disconnected algebra, a disconnected diagram. So it is a polynomial algebra over the set of closed connected diagram. If we have any algebraic structure, then evaluation gives us a character from this algebra, which we call the character of invariance. That just given any diagram, we evaluate it at A, and we get a number. So we get a homomorphism from this algebraic X-Og to K. Now, recall that before we had the algebra of invariance, KUD to the GLDK that we spoke about before. And the thing is that we have a natural map from this KX-Og to KUD to the GLDK. So from this kind of universal algebra that just has diagrams into the algebra of invariance. Okay, so first theorem is that this map is actually surjective, and this I proved using mostly sure-while duality. And the idea is, to show that everything in here you can describe using some diagrams. Of course, there is a kernel here that is quite complicated. Okay, so maybe one more thing I would like to say before that is just that, okay, so this algebra has infinitely many generators, and the kernel is also infinitely generated, and then we get this algebra here that we know just for theoretical reason that it is finitely generated algebra. It's an affine algebra. Nevertheless, we don't know in general how to get a nice finite presentation to it. Okay, so what does geometric invariant theory tells us? It tells us that if the orbit of some structure is closed in UD, then the character of invariant is actually enough to recover the isomorphism type of A, yi. But then comes the question, okay, but how do we actually do it? And now what I'm going to do is to tell you how to construct some symmetric monoidal categories out of the character, and then tell you how you can recover the original structure you started with from this. Okay, so let's write chi for the character of invariance. And recall that we have this kind of pairing for every P and Q, from con PQ tensor con QP to the algebra KXO. We can compose this pairing with chi, and we get a map from con PQ tensor con QP to the algebra to K by chi. Okay, and we say that an element F is chi negligible if it is in the radical of this pairing. That is, if whenever we pair it with something in con QP and apply chi, then we get 0. Okay, so now we construct a symmetric monoidal category Sikai in the following way. As objects, we take all objects of the form that we call WAB, which we will think of as W tensor WA times, tensored with the dual of W V times. The morphisms are all the constructible morphisms modulo chi negligible morphisms. Okay, so in other words, the morphisms in this category are only things that we can write using diagrams or as linear combinations of diagrams. And we declare chi negligible morphisms to be 0. And then we close this category under taking direct sums and direct summands, which is something that is relatively easy to do. Okay, so what are the categories Sikai? So here's a theorem. Let's assume that we started with some algebraic structure in VK, which is of dimension D, and it has a closed GLD orbit and a character of invariance chi. Then the Sikai, the category that we got here, is the representation category of the automorphism group of A, yi. Okay, so what do we mean by aut A, yi? So yi, I remind you, they are always just a bunch of tensors like multiplication, co-multiplication, a specific endomorphism, and so on. And an automorphism is a linear isomorphism from A to A that commutes with all the structure tensors. So for example, for multiplication M, it means that if I first do multiplication and then apply, let's call it G, or I first apply G and G to the two entries and then apply M, I get the same thing. This is exactly the same as saying automorphism of algebras, automorphism of co-algebras, linear endomorphism, something that commutes with a linear endomorphism, and so on. And the idea of proof of this theory is to really use the theory of Deligne. So I needed to show that in these categories, Sikai, you get things that are, all the objects in Sikai satisfy this finiteness condition that appears in the theorem of Deligne from the previous part. That is that a high enough exterior power is 0. And for this, you need to use what we know about about constructible morphisms and also about the negligible morphisms. Okay, and then once you have a fiber functor, you can understand that it is rep of some group G, and it's possible to show that the group G is exactly this thing. Okay, so this in particular implies that if we take Aij and we take the aut A invariant, then this is spanned by constructible elements. Okay, so what do we mean by this? So it's not so hard to prove that all constructible maps are invariant under aut A yi. And here's an example. So like, let's say I have this constructible map from before, going from A tensor A tensor A to A tensor A. If G commutes with M and with delta, I can just play a bit around with this diagram to show that this thing with G's in the beginning is the same thing as G's in the end. So it's not so surprising that all constructible maps are invariant under this automorphism group. But the upshot of this is that the opposite is also true. Everything that is equivariant under the action of this group is actually spanned by constructible maps. So we can reach all of these at once. Okay, and you might wonder what kind of categories can we get in this way? So the answer is that we can get any category of the form rep G, where G is a reductive algebraic group in this way. Okay, so by reductive, I mean that the representation category is semi-simple, and the nature of this is that whenever we are in a situation where Sikai is really a nice category, we yeah, we get that Sikai is actually already semi-simple. I will say something more precise in a moment. Okay, now something that is important to say here is that the construction of the category Sikai, this does not depend on the fact that Chi comes from a real structure. Remember, because we started with saying, let's say that that we have this kind of character coming from some structure in vector space, we can construct Sikai. But nobody forced us to take a character coming from this. We can just take any other character of this algebra. And describing characters of this algebra is quite straightforward in a way, because this algebra is a polynomial algebra. So we just need to assign values to all the generators, which are close connected diagrams. Okay, so we could carry this construction with any other character as well. And then we can ask what kind of characters do we get now? Okay. So what do we get now? So here's a definition. So a K-linear rigid symmetric monoidal category, which is the type of categories we are interested in. We'll call it K good if it's abelian and has finite dimensional Hopf spaces. And now we call a character good if it satisfies the following two conditions. Character from our universal algebra of invariants to K. So first thing, we want the radical of this pairing of con PQ tensor con QP to the algebra to Chi. We want this to have finite codimension. And second thing is that we want to be in a situation that if T is an nilpotent endomorphism, then in Sikai, then it will have trace 0, which is something that must happen if you want Sikai to be in a abelian category. So this first condition comes from the fact that we want finite dimensional Hopf spaces. The second condition is because we want an abelian category. Okay, and here's what happens is that if we have a character, then the following conditions are equivalent. First thing is that the character Chi is a good character. It satisfies the two conditions from the previous slide. And the second thing is that the character Chi is the character of invariance of an algebraic structure in some K good category. And third thing is that the category Sikai itself is K good and semi-simple. So that's the idea. I mean, if the idea is to show that if Chi is a good character, we can construct Sikai. And then because of the two conditions, we can show that it's K good and semi-simple. Then this is how 1 implies 3. 3 implies 2, because then if the idea is that the structure that we have in Sikai, it affords the character Chi itself. Yeah, and then we can also show that the 2 implies 1 or 3. Okay, so maybe before I continue, are there any questions? If not, then let me continue. Okay, so here's a question, because we know that we can get some good characters out of the, when you actually have some kind of structure, then you know that you can find the character and this will give you a good character. Now, here's the thing, can we find some good characters in any other way, So here's a definition. So a one parameter family of characters is just a collection parameterized by an element T in K, such that for every closed connected diagrams, it holds that Chi T of D is a polynomial in T. Why do we want polynomial? Because this way we can really apply things from algebraic geometry, and even not so complicated algebraic geometry, just even polynomials in some things we know about polynomials in a single variable. Okay, so here's what I could prove. Assume that Chi T is a one parameter family of characters. Assume also that there is a countable set such that S1, S2, and so on, such that Chi Si is good for every I. Then, under some mild assumptions, which I will not tell you here, Chi T is good for every T in K. So this enables us to pass from just a countable set to an uncountable set, to an infinite set of such characters. Okay, so here is a picture to illustrate this. This is our field K, And think of this as you have S1, S2, S3, S4, S5, and so on, these particular values. And then once you know that something holds for them, that is that you get a good character here and here and here and here and here and so on, then you get good character for all the points in your field. So let's start with seeing some examples, and this hopefully will make things a bit clearer of kind of what things we can learn from this. So let's start just with the case of an empty structure. Okay, so no structure tensors at all. And in this case, what happens is that the algebra of invariants is just polynomial algebra in one variable, which is the dimension invariant. And then this, all that we have in the constructible morphisms is either KD times SP for the symmetric group on P elements, and con PQ is 0 when P is not equal to Q. Okay, so we can write chi T for the character given by chi T of D is equal to T. And then for n in N, it holds that chi N is the character of invariance of the vector space K to the N without any kind of structure whatsoever. And then it follows that this Sikai N will just give us rep of GLN. Okay, but then what happens is that also Sikai T, this will also be a nice category with finite dimensional home spaces, and which is also abelian, and we call this rep GLT. Okay, and then since all the invariants are constructible, what we actually get here is Chauval duality. That is that the home in GLN between Kn tensor A and Kn tensor B is 0 if A is not equal to B, and is spanned just by applying tensor permutations if A is equal to B. So for example, by things like this, where we take the first copy of W to the to the third one, second to the fifth, third to the second, fourth to the fourth, and fifth to the first. Okay, we next consider the case of vector space with a non-degenerate symmetric pairing, because we would like to look at representations of the orthogonal group. Okay, so here we have C from W tensor W to K, and non-degeneracy of C is equivalent to the existence of a copairing, a map from K to W tensor W, such that this thing is equal to 0. So if I put one of the outputs of D to one of the inputs of C, then this is just, I get the identity of W. Now let's consider the theory of which contains the above axiom and the symmetry axiom for C, like we have here, just saying that, well, C of xy, x tensor y is C of y tensor x. And again, we have a certain ideal which we can divide by to that encodes exactly the axioms of this theory. And again, we get an algebra that is isomorphic to K of D. Okay, so just polynomials in one variable. And then using the same family as before, this chi T, we get that chi T is a good character for all T and K. We write C chi T is rep of OT. And these categories interpolate the categories rep ON. So you get an infinite family of categories, such that when T is equal to N, you just get the usual representation categories of the orthogonal groups. In particular, using again the fact that all invariants are constructible, we get this kind of description of a home, in this case ON from Kn tensor A to K. This will be 0 if A is odd. And if A is 2B, then we have this kind of description. I mean, just take B copies of the pairing and apply some permutations in the inputs. And again, a similar construction also works for the family of representations of the symplectic group. So this is roughly how such a constructible element will look like. We have, in this case, 3 copies of C, and we just permute however we wish the entries to the 3 copies of C. Okay, next example are the categories that I mentioned in the previous part of the talk, the categories that we call rep ST, Deligne. And in this case, we consider algebraic structures that are made of the following tensors. They are made of multiplication, unit, and C, which will be something like separability idempotent. And they should satisfy the following theory T of commutative separable algebras. So what do we have here? We have that multiplication is associative, it is commutative, U is a unit for the multiplication, these axioms just say that we have that C gives us a separability idempotent, sorry, in A tensor A or W tensor W. Again, direct calculation shows that all such things are the quotient of the invariant algebra by the ideal of relation coming from the axiom will just be polynomial in one variable. And this gives us, again, one parameter family of character. And when we take T is equal to n, chi n is just the character of invariance of the commutative separable algebra A, which is equal to k to the n. And we know that the automorphism group of that commutative separable algebra is just Sn, the symmetric group on n letters. Okay, because all that we can do is to permute the basis that we have of idempotence of this algebra. So it does get that Sikai n is rep Sn, and then Sikai t is what Deligne called rep St. So this gives actually a very different way to construct. Okay, I would say at least a different way to construct these categories of Deligne, because when he constructed them, he really needed to understand what's going on inside the category rep Sn. Here, the only thing that we need to know is that Sn is the automorphism group of this algebra, and it has this closed orbit. And once we do this, we can just interpolate by using this construction from invariant theory. Okay, another example was recently constructed independently by Khovanov, Ostrik, and Kononov. And this comes from two-dimensional TQFTs. This is the example of commutative Frobenius algebras. So such a structure is given by the following tensors. We have multiplication, co-multiplication, unit, and co-unit. Okay, and the point is that commutative Frobenius algebras, I still didn't tell you what the axioms are, but I will just tell you that commutative Frobenius algebras are actually equivalent to two-dimensional oriented TQFTs. Okay, so the idea is that whenever you have, so TQFT basically is a way to assign for two-dimensional TQFTs, to assign to every one manifold a vector space, and to every bordism between one manifolds a linear map between these vector spaces. And this there is this kind of equivalence with commutative Frobenius algebras, which is given by this kind of dictionary, where the multiplication is correspond to pair of pens in this direction, co-multiplication to pair of pens in this direction. U is and epsilon are half sphere. Identity is just a cylinder. Yeah, and C, I didn't write it here, but it's just what happens when we plug U into delta. So we get this kind of thing. And then what happens is that the closed diagrams are then equivalent to two-dimensional closed-oriented manifolds. And closed-oriented manifolds are just classified by their genus, right? So we get this kind of isomorphism now, that the algebra of invariance modulo the ideal coming from axioms is a polynomial algebra, this time in infinitely many variables, D0, D1, D2, and so on, where DG is a closed connected diagrams that corresponds to a genus G surface. And the corresponding character that we have is that determined by the numbers alpha G, which are just chi of DG. Okay, because when we evaluate, when we have a character on a polynomial algebra, it's just a bunch of numbers, like what it takes on the generators. Okay, so this is the theorem that Khovanov, Ostrik, and Kononov proved, is that the character chi is a good character if and only if, when we look at this formal expression, sum of alpha g x to the g, this is actually a rational function, and it is even a rational function of a specific sort. It is contained in the span of x and 1/1 minus lambda x. Yeah, they wrote it a bit differently with some condition on the degree of the polynomial in the numerator and polynomial in the denominator, but this is the same as saying that it's in this span. So the resulting category Sikai is the same as the category Dcob underline alpha that appears in this recent paper of Khovanov, Ostrik, and Kononov. So how much time do I have left?
10-15 minutes.
Yeah, okay. So I would just like, I think I will skip this part. It was another example from TQFT. I would like to speak about one more example about representations of the automorphism group of some modules and their interpolations. So let's say now that we have O, which is a discrete valuation ring with uniformizer pi and finite residue field. Think, for example, of ZP, the periodic numbers, or think about Taylor polynomials in a single variable over a finite field. We write Q for O mod pi for the cardinality of the residue field. Sorry. And then the thing is that we know that any finite O module is of the form by this fundamental theorem of modules over PID. It's going to be O mod pi to the A1 plus O mod pi to the R to the AR for some R, and where the AIs are just integers. So again, this is something that we can model as an algebraic structure also in the way that we described here. So how do we do this? We can get an algebraic structure by taking A to be Km, the span of UM. This is a Hopf algebra, and in addition, it is equipped with a collection of Hopf algebra endomorphisms of multiplying by O mod pi to the R. So we fix the R now. We just look for things that have depth at most R, so that pi to the R acts by 0. Okay, so the tensors are given by multiplication of UM1 with UM2 is UM1 plus M2. Delta of UM, well, it's a group-like element, so it's UM tensor UM. S of UM is U minus M. Epsilon of UM is 1. U of 1 is U0. This is the unit. And the X of UM is UXM. Okay, so, and then if, here's the thing is that if Chi is the character of invariance of A, then for every closed connected diagram, it holds that Chi of D is actually some power of Q. And moreover, it's a power of not only of Q, but it's going to be a product of Q to the A1 to the C1 times Q to the A2 C2, plus times Q to the AR to the CR for some CI in M. Okay, so in other words, we can write Chi as a character that depends on Q to the A1 up to Q to the AR. And then for general T1 up to TR in K, we can just define it exactly the same way, that Chi of T1 up to TR of D is equal to T1 to the C1 up to TR to the CR. Okay, so in this way, we move from the case that we only have powers of integer powers of Q to just general complex numbers or elements of K, if we want to work on with a more general field. And then what I showed is that for every T1 up to TR such that are all different from 0, the character Chi T1 up to TR is in fact a good character. So in this case, we can kind of interpolate the family of these categories into something much, much bigger. And yeah, it enables us also in a way, of course, again, we cannot really talk about something like Z mod P squared to the power of square root of 2. That makes no sense. We can also not talk about the automorphism of Z mod P squared to the power of square root of 2, but we can talk about the representation category of the automorphism group of this thing. This already makes sense, and this is what we construct here. Okay, so this construction generalizes a construction given by Knop, but specifically for free modules, that is for he constructed things like rep of GLT of O mod pi to the R. It also enables to describe the Hom spaces in a concrete way using sums over some homomorphisms from random O mod pi to the R module into M. I will not explain exactly the way it looks like, but there is a concrete description also to the constructible elements here, which are all the OT KM invariants or OT M invariants. Last thing I would just like to mention before I finish is the following, that if you write P for the set of closed connected diagrams, I mean, all these examples, we might ask how big or how general this set of good characters is. So here's the thing, that let's say we can write, if we write P for the set of closed connected diagrams, then since our ring is actually polynomial algebra on P, any character can be considered as a function from P to K, right? Because, well, this is what a character does. It just assigns values to the generators. Alternatively, it's an element in the algebra K to the P. And then we can ask, what does sum and product in k to the p mean for characters? And this is the thing, that if A has character chi and B has character psi, then we can talk about the direct sum, and this has character chi plus psi, and the tensor product will have character chi times psi, where sum and product are taken in this algebra in k to the p. And then by considering the category Sikai tensor C psi, we see that we can show that the set of good characters is closed under taking direct sums and direct product and tensor products. And here's the thing that we need to work a bit harder, is not only that it's closed under sums and products, but in fact, the set of all good characters forms a k-subalgebra of k to the p. Okay, so this is already, I mean, it has a bit more structure than just some subset of k to the p. Anyhow, so this is all that I wanted to say, and thank you very much for listening. Thank you.
Thank you very much. Yes. Are there any questions from the audience? Yes, Eli.
No, I didn't. In fact, I have a question, but I didn't. Hello, Hudi, how are you?
Hi, good. How are you?
If you want to do descent theory,
Yes.
I mean, together with this enormous structure that you mentioned. So what can you say? Is it possible? Is it straightforward?
So some parts will be straightforward. So for example, like let's say that I start with an algebra in a non-algebraically closed field. I can still talk about the invariants. I can still construct this category Sikai. The only thing is that, okay, the values of the character will be inside the field I started with, and probably in something smaller. Then what is not so clear is if I will get a fiber functor to vec k, where k is the field I started with, or maybe to vec L, where L is some proper subfield. So, okay, so I mean, this thing has something to say about descent, but I mean, I'm not sure if it's a satisfying enough answer, like in the sense that, like, let's say that if I look at the field generated by all the invariants, let's call this L. So I get that this category is defined over L, but it doesn't necessarily mean that I have a fiber functor from this category to vec L, because that would mean really a form. So it's a kind of situation where you have this necessary condition that is all these scalars should be inside there, and then if you ask, okay, but what can be done over L? So the answer is what can be done over L is exactly the construction of this category, but perhaps not a form.
I see. Okay.
Thank you. Other questions?
I have a question. Hi. So I wanted to ask you whether this construction gives you any kind of universal properties for your categories. I'm sorry, maybe you said it, but I didn't understand it from that.
No, so I avoided saying that. Okay, so the thing is like this: in the original construction by Deligne for RepST and also some of the other ones, what he did, he didn't kill all the negligible morphisms at once. You just kill the morphisms that arise from the axioms, and then you do get a universal construction. You do get a universal property. Now, in our case, you don't get a universal property, only that in some cases you actually do. So let me, just to give you an easy example, like you can show, and it's not a lot of effort to show, for example, that, wait, maybe I can share my, I have this kind of document camera, which will make it a bit easier to write things down. Yes, well, it's, okay. Okay, so for example, you can find, let's say you have T1 plus T2 is equal to T, then it will be possible to show that you get a functor from rep ST to rep st1 tensor rep st2, and also from things like rep of GLT FQ to rep GLT1 FQ tensor rep GLT2 FQ. And the same also for the more general categories with the diagonals. So here's the thing that one of the questions that I know that Deligne asked in the original paper was about the singular values, right? Like for what values do we, and because here you have a very concrete description, at least in these cases, you get a very concrete description using the constructible morphisms, then you can actually calculate the determinant of some matrix and see exactly what are the singular values, and then you say, okay, but if I'm far away from the singular values, then everything is fine. I don't need to worry that much, and then you still have this kind of universal property. But it's okay, but it's definitely not the case that because we did this division by negligible morphisms, then it's not the case that you have the most general form of what do you want to say? The most general form of universal property. So, for example, if I take let's say an endomorphism T from W to W, such that let's say trace of t to the 0 is 1 and trace of t to the n is square root of 2. This is for every n bigger than 0. Yeah, then allegedly I get here a vector space of dimension 1, but I really will not get a morphism from rep, a functor from rep GL1 to Sikai in this situation. And why not? Simply because, you know, it's okay, it will be a vector space of dimension 1, but it will split as the direct sum of a vector space of dimension square root 2 with a vector space of dimension 1 minus square root 2. And then it, yeah, and this will make the possibility for a functor to fail, like that lambda, like this condition doesn't hold anymore because of this. Yes, so in general, there aren't any universal properties, but in some situations there are.
But will you get, for instance, a functor from rep GLT to rep ST?
Oh, that's an excellent question. I try to construct such a functor, and the thing is that, okay, the answer is in general for generic values of t, the answer is no. And I can tell you why. The reason that the answer is no is because, okay, like if you have, like let's say I have in rep GLT, it is generated by an object of dimension q to the t, right? So this is a GLT FQ. On the other hand,
I actually meant over the complex numbers. So if you just take GLT over C.
Yeah. Whoa, wait. So just a second.
Yes.
Then you get a functor. Yes, for generic T you do. So okay, sorry, I didn't understand. I was summarizing. So from GLT-C, so from rep GLT-C to rep ST, you do get, yes.
So this you get it from your construction, right? Just
yes.
By,
Yes, and the idea is just okay. You take the generating object here to the regular representation, like not regular, but the permutation representation of ST. Yes, so this does work, and you can show that for generic T you do get such a functor. Yes.
Thank you very much.
Thank you, Seydon.
Yes, I have a follow-up question to the descent question. So maybe in the sense that if you have something defined over a bigger field, well, if you have two fields K and L is an extension of K, can you express things defined over K as things defined over L with some extra data that somehow encode this descent?
So you say K is an extension field of L?
Okay, sure. Then in that case,
then also the other way around. It's
All right.
Okay, so L is an extension field of K. Yes.
So for descent, I mean, you would have something defined over K. Instead, you can define it as something defined over L with some extra data encoding this descent.
You mean like the twisted Galois action?
Something like that, yes. Is
Yeah.
there anything? Is this compatible with your formalism?
To some extent, yes. So, well, here's the thing. That the first thing is that you get this kind of I will use again Kx aug, but I mean let's just call it Q x aug for the time being. I mean, you do get a character from here to L. And then first question is, okay, is this the case that the image is actually contained in K? If it is not contained in K, then you have no chance whatsoever. Right, so let's assume that it is contained in K. And then what happens is that the category Sikai is actually already defined over K. And then the thing that corresponds to what you say, like, okay, to actually give a form over K will be the same as to give a fiber functor from Sikai to vec K. And okay, so the idea is that even though the definition of Sikai, like the representation of the automorphism group of the object, that goes down all the way to K just by this condition, that the chi of this thing is contained in K. It's not clear that the fiber functor goes all the way down in this way. So in the original thing that Deligne did, he used algebraically closed field pretty much for this reason, that he showed that also that the fiber functor is unique. And the uniqueness really relies on the fact that that you have something algebraically closed. And over algebraically closed field, you only have one form, right, of everything.
Yes.
Yes.
And you cannot, there is no way to realize fiber functors over smaller fields or to smaller field to vec K for smaller K in terms of fiber functors to vec L with some data.
Good question. Let me think.
It's not obvious, at least.
It's not. No, it's not obvious. It's not obvious. I mean, it's this kind of very confusing because, okay, so I mean, like let's say you say that the fiber functor on, you know, when you actually go down to see what describing the fiber functor is, it really is like finding the forms of the structure you started with. So.
Okay.
Yeah.
Yeah. Okay. I see. Yes. Thank you.
So I'm not sure. I mean, it gives a description of the same problem, but in kind of a different language, like with.
Okay.
Yep.
I see.
But it's
Thank you
still.
very much.
Thank you. Are there any other questions?